Do we have questions on the homework?
There's something about like what's that called? There's like a you know, I got the answers like.
How do you enter the LaTeX stuff in?
You just type it in or use a template.
No, it's not that easy. Like, yeah, if you want to show your work on the whiteboard or something, you can't do it. You can't upload, and it gives you an option to upload graphics, and you can't do that either.
Oh,
It wasn't
I'm not
submitting.
sure about that. I never actually tried to show your work feature, so I don't know. Maybe ask
But
him.
there's also, there's a place, actually, there's in chapter 1 where you enter your answer. It was c e to the negative 2t, and it wasn't easy to put my answer in.
Did anyone else have that problem?
Oh yeah.
Everyone did.
Yeah? I don't think it would be that hard. I thought you just type
No,
it in.
you had choices of LaTeX or HTML. You didn't have a template.
Well, I've been on it. I've seen the template, so I'm not sure what you guys are.
I'll show you after class.
Yeah, I guess someone else was going to show me after class what they meant, but when I looked at it, it seemed fine to me, and there was a template and everything, a drop-down menu, and I could just type into it.
Maybe it depends on what system you're using. I'm using
Maybe the
Mac.
browser. The browser could affect it also. Maybe.
I tried it in 3 different browsers.
You gotta update the flash because I was getting that issue. Like when you wanted to enter it, it was this is like a box that was empty. Yeah, you gotta update the flash. That's what
Yeah, I
it
did
was.
that. It's
So
like,
I don't know.
are you on a Mac?
I tried it on the Macs here, and it told me to update it, so I just went home and I used it on a PC. Yeah.
Yeah, it did. I'm on a Mac and it didn't work.
Yeah.
Well, someone has to see me and show me that, because when I checked it myself, it worked for me, so I don't.
You don't have a Mac.
PC.
Any questions otherwise, though, other than mechanics of entering your answers?
Well, that's kind of key in order to do the homework. You know?
But you can get the answer, but you can't plug it in. It doesn't mean jack.
Right.
Yeah.
Those are the equations that was like u sub x plus 4 u sub x plus y.
XXX.
4x plus 4
Plus.
u sub xxyy plus u sub y equals u.
What is that?
What is.
It was asking for the order.
The order
Oh.
is it's linear.
Yeah, it should be the fourth order.
Oh, yeah, it's just.
Oh, fourth order. Okay.
Remember, the order is just by the highest derivative.
Okay.
You're just looking at the highest derivative. It's just partial derivatives here. So.
No,
Oh, okay.
I've never seen an equation like the sub xxx.
It's from like Calc 3 notation. This just means partial u for dx for the fourth partial derivative.
And the middle one?
U sub xxy.
This is like u4 dx squared dy squared.
Oh.
It's like you take two derivatives with respect to x, then you differentiate that twice with respect to y. Right. We're going to look at equations similar to this like towards the end of the course. Not that many partial derivatives, but something similar. But yeah, the order is just defined by the order of the derivatives.
Also, there was one question in chapter 1, section 1.3, problem 20. Determine the values of R for which the given differential equation has solutions.
Chapter 1, 1.3, problem 20 in the homework.
Yeah. I entered 7.
Wait, what was the question?
No. I was just wanting to say that it gives you an error. Does it matter like which way you enter the value of R?
It says there has to be in order.
Yeah, they'll give you an order if it matters. They'll say enter in ascending order or something.
No. I'm just scratching my head.
Okay. Any other questions? So I guess the math itself was easy, the hard part was like entering it.
Basically,
Okay,
can
cool.
we go over section 1.2, question 19?
219.
Also, can we hand the homework in handwritten to you?
Because then
We
we
have to do it online.
Okay, 1.2, problem 19. Your swimming pool contains, what is this number you're writing over here?
70,000.
Okay, it contains 70,000 gallons of water. You have 5 kilograms of non-toxic dye. The pool's filtering system can take water from the pool, remove the dye, and return the water to the pool at a flow rate of 200 gallons per minute. What is the initial value problem for the filtering process? Q of T is the amount of dye. What is the initial amount of dye in the pool? Okay, so what do you think the answer is? So it contains 70,000 gallons of water and it's 5 kilograms of non-toxic dye. I guess we can work in kilograms. Well, they ask for grams here. So you already know Q of 0, that's the easy part. So we want to work in grams. How do we find, take water from the pool, remove the dye, return the water to the pool at a flow rate of this? How do you think it will work?
conversion.
What exactly is the question?
The initial.
You have a pool that contains 70,000 gallons of water. You have 5 kilograms of dye in it. And there's a filtering system that is taking water out the pool and putting fresh water in the pool. And now we want to know how to set up a differential equation to
Put the
model
dye.
that behavior.
I think we're gonna use the rate.
But are you putting the dye in the pool or taking the dye out?
Taking the dye out.
Okay.
As Q prime equal R Q. Like the population.
No.
Find the amount of dye per gallon.
Choose the amount of dye. So focus on the dye. How is the dye changing?
It's diminishing.
Functional.
Well, we're actually going to cover this more in section 2.3, but basically the idea is figure out how much is coming in, subtract how much is going out. Right? How much dye is coming into the pool? 0, right? Because we're letting the mixture flow out and we're putting fresh water back in. So there is, in our process, there's nothing coming in. But how much is going out?
5 kg divided by 70,000 gallons times 200.
What's the rate at which it's coming in?
Coming in at 200 gallons.
200 gallons per minute. Now, in each of those, how much salt is contained in it? Or dye?
0.
This is what's going out, so we definitely
Oh.
have some dye in it.
5 kilograms divided by 7,000.
25. 25 gallons. 25 very high.
It is Q over 70,000. It's 70,000 gallons. Do we see why it's Q over 70,000?
That's the mixture.
Lowercase q.
Is that like the concentration?
It's the concentration, right? This is the amount of salt, the amount of dye currently. Usually these problems have salt. this is the amount of dye currently in the pool, right? That's Q of T is the current amount. And this is divided by the volume. So you have this much per gallon, and you have this many gallons coming in, right? Now we don't know what the Q is. That's why we just have to write Q. Ultimately, we want to solve for it. But basically, we have to figure out how much is coming in versus how much is going out. You take this minus that. There's nothing coming in because there's only fresh water. We have 200 gallons per minute coming in. And we have this amount per gallon in each of those gallons, right?
So
One
we
way
also have to do a conversion into
Yeah.
kilograms, don't we?
to yes,
Big
but
gallons.
so far we're
To
doing
liter.
gallons.
Okay.
Yeah. So I already did the conversion.
Okay.
But another way you can see this to make sure you're doing the right thing is to look at the units, right? You have 200 gallons per minute times Q grams per gallon, right?
So, it's gonna be grams per minute.
So then this would cancel, and this tells you how many grams is coming in per minute. And that's the rate of change of dye per minute, right? And so basically you end up having to solve the first order differential equation minus 200 Q over 70,000. This can go into that. Which is separable and you can solve, right? With this initial condition, because we're thinking of it in grams. We're actually going to go back over this, and I'm going to do this in detail, how you actually compute these parts later. But they just wanted to get you thinking of it ahead of time, I think. All right, other questions? Yeah.
We don't consider the volume of the dye. Say for, I know the volume of the dye here is quite minimal, but
Yes, we do consider the
But then-
volume. The thing is, what's going in is the same as what's going out, so the volume is actually constant.
Okay, sure.
There are cases where it will change, and how that will change the equation is this part, which will depend on T.
Okay.
Yes. But in this case, it says it's replacing it and removing it at the same
Same
rate,
rate.
so our volume is constant. We don't have to worry about any change in volume. That's why we have this. Other questions? Yes.
For this ball, there's like 4 parts. Like, can you go over like the velocity?
Oh, you didn't give me this page. Okay. You invited the 5 hours. You invited several dozen friends to a pool party that is scheduled to begin in 5 hours. You have to determine that the effect of the dye is imperceptible if its concentration is less than this per gallon. Okay, so we'd actually have to solve this. So this is dq over q is equal to 3 minus 1 over 350. This means ln q is equal to, this ln q is equal to minus 1 over 350 t plus c. This implies q is equal to c e to the minus t over 350. And now we apply the initial condition. So when t is 0, q of 0 is 500. This means 5,000. And so that is the amount of dye in the swimming pool at time t. And we need to make sure that the concentration is less than 0.017 grams per gallon, right? So how many grams should be in the pool? I want a concentration of 0.017 grams per gallon. So you just take 0.017, you multiply it by the amount of gallons in it. What's that?
A lot of calculators, somebody.
We often need it for the homework. What's that?
No, that calculator.
No, it's not, told us not to bring a calculator, so.
Wait a second.
1,000, 190. And then, so this means if we set this to the amount of salt we want in the tank, and then, so we get T equals, you know, whatever. And this would be the time needed to filter the pool enough. Right? And of course, remember your units. I think the time here would be in minutes. You have to change it to hours and see, is it greater than or less than 5? And then you can answer the question based on that. So you want to filter the pool to have a certain concentration. So you figure out how many grams you need for that concentration and set it in for Q, and you can find the time needed to get to that concentration. If it's more than the 5 hours, then you can't filter it by the time your friends come in. Find the time T where the concentrated first reaches this. Oh, wait. Well, it's this. And find the flow rate R sufficient to achieve that within 4 hours. Okay. So everything can be answered up to what I did here. To answer the last question, though, you're going to have to redo the problem, sort of.
Well, that's a lot of work for one problem.
You haven't seen anything yet? It's very characteristic of this course. A lot of the problems take a long time. Which is why your calc 2 and your algebra has to be on point, because you can't waste time on things like that. So the idea is we had Q prime is equal to minus, there's some R that we don't know. And basically solve for Q. Set T equals 4 hours. Find R.
Why 4 hours?
They ask you, right, what does the flow rate have to be to get to that concentration in 4 hours? So it means here you don't know what the flow rate of the filtering process is. So you replace it with R. You do exactly what I did over there. Plug in your initial condition, and then you set, this is the amount of grams you want, this is the time you want to be there, and then R will be your only unknown in the equation. You just algebraically solve it. Questions on that? So in the end, the equation would look something like Q equals 5,000 e to the minus R over 70,000 T. Right. Then plug in 1190 here, plug in 5,000 there, e to the minus 4R over 70,000. Well, our time was in minutes. Depends on how you want to set up your time. T in minutes. Depends on the units, you just have to. And now you just solve for R, right? So you divide by this, ln both sides, blah, blah, blah. I guess, are there any more questions? All right, let's continue. So last time we started talking about homogeneous differential equations. I think we only did one example. I'm gonna do a couple more before moving on. What can you remind me about homogeneous first order differential equations?
The function of x and y will be the function of kx,
All right, so the ODE dy dt equals f of ty, or if you want to use x, that's okay, is homogeneous if f of xy is equal to f of kx. Okay, all right. Then what do you use to solve such a differential equation? Use a substitution, which is
1 from b, where x and y.
B is equal to 1.
b equals y over x. Then set dy dx equals, and your f of xy equals, what would dy dx equal?
b plus
And then this one becomes f of 1 comma b. Right? All right. So that's how we solve these guys. So let's do an example. So if you see this on a test, what do you do?
Times its top and the bottom by 1 over x squared.
the check is homogeneous.
That's what you do. So you're on a test, and this pops up. What do you do? What's the first thing that goes to your mind? Huh? Is it separable? That's the first thing I would think.
Really?
See this? Because it's separable. No, it's not separable. Okay, what else would you think?
Separate the fraction, see if that helps. Make it 3y squared over 2xy minus x squared over 2xy.
I guess you would do that to try to find out if it's linear, but it's not, which is the second thing I would think. Could I make it linear? Again, the answer is no. Then I think, is it homogeneous, right? And so we would quickly do the check. If I replace the y with ky, the x with kx, it turns out that this would actually be equal to the same thing. So it's homogeneous. We're not cheap just because we're doing homogeneous. I don't just like, oh, it's homogeneous, right? There's a thought process that you're going through. On an exam, I'm not going to tell you it's homogeneous. You have to figure it out, right? I give you a first order differential equation. The first thing you think, can I separate it? Is it separable? That doesn't work. Is it linear? Because I know if it's linear, what do I do? Integrating factor. What's the integrating factor?
Mu.
Mu equals
E to the
e to the integral of p. What is the p?
Coefficient of y.
The coefficient of y in what form?
The standard form of y prime plus or minus p of
P of
y.
t and then y
Equals some other function. Right. So if you can write it like this, it's linear. You just find the integrating factor, multiply it through, it turns this sign to the product group. Okay. All right. So we're not just blindly doing things here. We have to learn the thought process, because I'm going to give you a bunch of ODEs to solve, and I'm not going to tell you what technique to use on which. So keep in the habit of knowing how you want to approach these things. It's also why I wrote down these steps, right? So once you identify what kind of equation it is, you should automatically, steps of how to solve it should automatically pop into your head, right? If it's separable, you separate them, integrate both sides. If it's linear, multiply by the integrated factor, which is e to the integral of p, and it turns the left side into the product rule. If it's homogeneous, which means it gets through this check, then you do this, right? Like this should go through your head in a split second. Because in the exam, the algebra is going to take a lot of time. Like I said, the questions will eventually get really long. You're going to need the time to work out the algebra. You should be spending no time trying to figure out what to do, right? Okay. So I'm given this. Is it separable? No. Is it linear? No. Okay, maybe check homogeneous. Works out. So now that it's homogeneous, this guy will become, by our substitution, v plus x dv dx equals, this side, everywhere I see an x, I put 1. Everywhere I see a y, I put v. And I end up with that, right? Which if you divide top and bottom by 1, if you multiply top and bottom by 1 over x squared and then do the substitution, you get the same thing. You'd end up here eventually with less algebra, more algebra. Okay, how do I do this? Subtract the v from both sides, right? That's always what you do. And what do I do now? What's the next step? How? Common denominator, right? So you have 2v over 2v. So this gives you 3v squared minus 1 minus 2v squared all over 2v. Right? So this means you have x dv dx equals v squared minus 1 over 2v. And so this means 2v over v squared minus 1 dv is equal to dx over x. Right? So it's separable. And so now I'm just going to integrate both sides. What's the integral of the left? ln v squared minus 1 by substitution equals v squared minus 1. This side gives you ln of x plus c. Which means here you can rewrite the v squared if you'd like. So this is y squared over x squared minus 1 equals ln of, this I can write as some other constant times x if I so choose. This means which case I can do something like this. Right, just multiply both sides by x squared. And I can take that to be the solution. All right, you see this on an exam, what do you think? Is it separable? Is it? No, because of this guy right here. Once you try to move the x over there, it's going to mix up with that guy. So it's not separable. Is it linear? No, it's not linear because there's an ln of a y. Okay, so it's not separable, it's not linear. So now we're trying to check, is it homogeneous? How do we check that? Huh? Okay, but it's Probably easier to write it in a nice form first.
Take the long together.
We combine it to make it y,
ln of x over
ln
y.
x over y.
So we have x y prime equals y ln x over y, right? Clearly now if I replace x with kx and y with ky, the k's just cancel here. That makes no difference. If I put a ky here and a kx here, it can cancel from both sides, right? So homogeneous. X to kx and y to ky makes no difference. So it's definitely homogeneous. So what do? Well, everywhere I see x, I'm going to put a 1. Everywhere I see y, I'm going to put v. Where I see y prime, I'm going to put v plus x dv over dx. This will be v times ln of 1 over v, which is v plus x dv over dx minus v ln v, which is x dv dx minus v ln v minus v. Come again?
On the left side, there is an x that you there was an x with the y prime.
Yes, which it turned into 1. Right? You divide both sides by x to get that. Y over x. Now what?
We used to try here. The first one.
Is it separated yet? It's not separated yet. I have these and x's mixed up on one side. How do I separate it?
You divide by, well, you divide by v on both sides, kind of keep x over dx, and then just
Yeah, but I have an L and V. How about we divide by this whole thing? So I would have 1 minus 1 over v ln v plus v dv equals dx over x. And of course this is separable. We're going to integrate both sides. What's the integral of this?
Should that be a subtraction? ln of b minus b.
When I bring,
Oh,
I factor out the negative sign and divide. Yeah. How do I integrate that?
yeah, use substitution.
Substitution. Right. What would you substitute?
ln v and then
ln v, because we can factor out the v.
You can factor out the v. What do you substitute?
V ln v.
No.
ln v plus 1.
ln v plus 1, right? You do a substitution of u equals ln v plus 1, and then you'd end up with minus ln of ln v plus 1. You guys are taking too long to figure that out. Okay, now what? Well, right now it's a matter of algebra, right? You just start solving for stuff. Right, you can just rewrite this with ln of x over y. And that's good enough.
there you go.
Yes.
Yeah, if you like go about a problem all wrong, like you look at it and you just misclassify it or whatever, like is there gonna be a certain point where you'll realize, or you'll just get the wrong?
Yeah, like something would break.
Something would break.
Yeah. In general, it's. So, yeah, that's it. I did want to mention something though. The idea of substitution. And work in general, if the conditions are right. For example, we could solve So if you see this on an exam, what would you think?
Separate.
Is it separable? Is it? No. Is it linear? No, because the y is going to get squared. Is it homogeneous?
Try it.
If I put a k here and a k here, does it make a difference? Would all the k's cancel out and then I get back the same thing? No, so it's not homogeneous either. But it turns out for something like this, you can still use a substitution method. What do you think would be a good substitution here? Turns out v equals 4x minus y can help you solve this stuff. And then you figure out, okay, if that's the case, what does dy look like? And you replace this, and then you replace this with
Wait, how do
this
you know
whole
though?
thing will replace v.
What did you
Like,
get?
like
V?
how do you know though? Like,
Well, what was the idea behind substitution when you were learning integrals? You had something, and it looked complicated because there was this whole thing in there, where if you substitute a whole expression for a single variable, it's somehow simplified to a nicer form. That's the idea. If you can somehow express your ODE to be expressed as a single variable replacing some troublesome part,
okay.
then you can use that idea to your advantage all the time. It was sort of what happened when we were thinking of homogeneous. We realized that we could actually express the function. We could actually take f of xy and sort of isolate the variable x over y. Well, y over x. Right? Where we could take this and we can sort of see that, oh, if I replace y over x with a single variable, it simplifies it to a nicer form. Right? That was sort of the idea. And sometimes you can actually see that in general. For this course, the homogeneous substitution, I think, is the only one you need to know. I don't think you'll see anything like this, but just know, like, the technique is out there and is a lot more general than we're showing you in this course. So I just thought I'd mention that. Try this on your own and see if you can get the solution. I'm not going to go through it. But that does it for 2.2. Going to start 2.3. I wanted to do those tank problems, like the pool problem that you guys asked me at the beginning. I wanted to do that in general, but I don't know if I have enough time to go through all of it. Or should I just do this other thing and call it a day and pick that up next time? It's all in 2.3. I'm just wondering which part of 2.3 to cover first, because I can't finish everything. So we're going to do 2.3, which is modeling with this order leading to the east. And we're going to do some selected applications. covered money population applications. You guys remember what we did here? What was the ODE that described the balance in a bank account being compounded continuously with interest rate R? P prime equals RP, right? And you can make it more general. H or K, I don't know. Depends on what textbook you look at. You can make it more general by adding or subtracting something per unit time, right? So we already did some stuff with that application. Another application is the mixture problems, this idea that you have a tank with some pollutant in it and you're trying to filter it and how long it will take and all that. That's a whole other application. Like the more generalized version of that pool example that we had in the beginning. When I do it, I'm going to do it in detail because I'm going to assume that you guys probably don't know what concentration is. I'm going to have to explain concentration in units and all that. Make sure you guys are on the same page when we move on. So instead, what I'll do is I'll do another very small application, and then we pick up with the mixture problems next time. Newton's law of cooling. It's actually something you saw in Calc 2 before. Now I'm just going to remind you of it. With one example. So the law says the rate of change of temperature of an object is proportional to the difference in the current temperature and the surrounding temperature. I'm not sure how Newton figured this out. He's a smart guy. He figured out a lot of stuff. I'm not sure if there's a mathematical derivation or it was just like experiments where he actually just measured this all the time, but that's the law and it seems to work out pretty well. And based on the wording, you can come up with a differential equation for it. If t is a function of time, is the current time at time t, if t ambient temperature. T equals time. Then you could actually say the rate of change of temperature is proportional to the difference between the current temperature and the surrounding temperature. This ODE is called Newton's law of cooling. It describes how the temperature of an object cools down and what rate the temperature changes. Yes.
What's the case now?
The K is just a constant. Like, given an initial condition, you'll solve for it. So it will vary with the material of the object and all that. So that's basically the law. And of course, we can solve this and figure out what T is if we're given enough information. So, do I want to solve this in general? How do you solve an equation like this? Right, it's separable, right? This side here is d big T d little t equals minus k t minus t a and b. Right, this is assumed to be constant as well. Otherwise, it becomes a lot more difficult.
So you not pick first like the initial condition?
When you get to a problem, we'll give you initial condition. I just want to solve this in general. What would it be? So it's a first order ODE. The first thing we think, is it separable? Is it?
Yes.
Yes, it is. How?
You can divide t minus t and
Right.
both sides
Divide both sides by this guy.
and multiply d lowercase t.
Right. And you get that, and you can integrate both sides. This gives us ln t minus t b equals minus kt plus a constant. This means t minus t a and b is equal to a constant e to the minus kt. This means the temperature is equal to c e to the minus kt plus t a and b. So for most objects, that describes the temperature change if you just leave it in some constant temperature surrounding. And we're going to do one example in this, because again, it's not really a focus in this course, but it's something you should know. So we'll only do one example on this, and then we'll move on to more applications next time. So I'm handing out the list of examples we're going to be doing for 2.3. Most of them are word problems, so I don't want to be writing them out on the board. So I thought things on this page that have an asterisk, those are the examples for 2.3. And the one we're going to do now is the last one on the back. That's a Newton's law of cooling problem. The original wording of the problem was really fun, but then I had to make the language PG-13, and then it didn't sort of fun. Not fun anymore. But you get the idea, right? So here's the problem, right? Guy impregnates a girl, and her father finds out. So he's very angry, right? He's visibly angry. Everyone knows this guy's father, the girl's father, wants to kill this guy, right? Next day, the guy's found dead. They think it's from stabbing. They find the knife in the guy's hand, right? So the parents, they blame the dad. They say, you know, he was angry, he killed our son. There's like, no, he had a knife in his hand, he committed suicide because, you know, he was like all worried about his future, right? But what you know about the case is the following, right? He was found dead in his air-conditioned room, which was maintained at 60 degrees Fahrenheit, right? He had the AC on, he liked it cool, right? Now, they measured the temperature of his body when he was found, that's 80 degrees Fahrenheit, right? And they measured how his body cooled down. At some point later, it was 75 degrees Fahrenheit, 2 hours after he was found. They found him at midnight, and the father's alibi is that he was at work until 8 p.m. He couldn't have possibly killed the kid, right? Now they turn to you and ask, you know, because you're a mathematician by day and crime solver by night. They ask you, what is your opinion? Did the father do it? What do you think? Right?
It's probably ripped off.
So now you have to solve this problem, right? And the clue that you would use as a mathematician is the temperature change. He was found at midnight. His body temperature was 80 degrees Fahrenheit. 2 hours later, it was 75 degrees Fahrenheit. The surrounding temperature was 60 degrees Fahrenheit. So basically, we want to figure out what is the rate of his temperature change. And we could sort of try to figure out at what time he was killed and sort of see, could the father have done it? Is the alibi a valid one? That's going to be the idea. And of course, we have to know the normal human body temperature, which is about 98.6 degrees. We're basically going to use this method to figure out when was the body at 98.6 degrees, which was the last time this kid was alive. So, how do we go about it? Well, start out with this differential equation. What do we know so far? Well, the only thing we know so far is this. We have some initial conditions we'll plug in at a later point. So we have that, and then we're going to go through this whole thing of solving it, right? We already showed how we were going to solve this, and we're going to get t is equal to ce to the minus kt plus 60. Now notice here we have two unknowns in our equation, which means we need two pieces of information to be able to get any sensible answers from this. And we do have two pieces of information. What are the pieces of information that we have?
Can we use t as 80 degrees like that?
Depends, when.
We have a constant temperature.
So first we have to set our clock somewhere. It was found at midnight, set that to be t equals 0. Right? In other words, we know that t of 0 is what? It's 80. Do we know t at any other point?
Yeah, at 2 o'clock in the morning,
At 2 hours later, right? If I'm measuring t in hours,
it's 75.
that means it was 75 2 hours later, right? So I have two initial conditions and two unknowns. I can actually find them, right? This one would mean if I plug in little t equals 0, the big T should be 80. So this is 80 equals c plus 60. This one would mean 75 is equal to ce to the minus
K2.
2k or k2 plus 60. Now, this means c is equal to what?
20.
C is equal to 20. This means that you have 75 equals ce
20.
20e to the minus 2k plus 60. And how would I find k now? Subtract the 60. Divide by 20. You can ln both sides. So this means your k would be equal to minus, this is ln. I can take 5 into 15 goes 3 over 4. All over 2. Probably
So
get her.
now if we set t
So-
to 98,
This means t is equal to, where are we? 20 e to the minus,
ln 3/4 over 2. 60.
60. That will be the temperature change. Okay, so,
Yeah, would it be positive since it's negative?
No, because we're going backwards with the temperature.
it was a minus k, yes, so this would be.
Oh, okay.
All right, so now what? How do we figure this out?
Plug in 98.6. And solve for t.
And solve for t. What is the solution here? It's 38.6 divided by 20 equals e to the ln 3/4 t over 2. Ln both sides. This means t would be ln of 38.6
Over 20
over 20
divided by
times 2 divided by ln of 0 over 4.
Wait, where did the, oh, I see it there.
What is that?
No, I was gonna say, where did the 2 come from, but I see.
Yeah, sure.
Have like a calculator.
One time we needed a calculator.
No. But I wouldn't ask you like something like this in the exam.
Something graphic calculator.
So no one has a calculator?
You told us
You told us not to bring
a
that.
calculator.
Not for exams. The syllabus that says homework and stuff like that might have these calculators.
Yeah, but never mind.
No excuses, Vincent.
No, 1, 2, and 3 we were told not to bring a calculator, so we just kind of anticipate this class don't bring no calculator.
So wait, for the homework, we're allowed to use a calculator?
Yes.
Yeah, no wonder was so damn
Look at
hard.
that swimming pool one. You can do that. This one is like stay forever.
Can anyone possibly do this without a calculator?
I'm sure they can, but
Well, for our purposes, we would sort of need it. We need to know what this number is.
It's negative 4.57.
Negative 4.57, roughly, right?
He didn't do it.
So what does that mean?
he didn't do
He
it.
didn't do it.
Kid died 4.57 hours before midnight.
So the alibi checked out.
But
Could have hired somebody.
but did he stay at 8 p.m.? Did he?
The alibi is worth checking out. It's not like, no, he's lying. No, we need more investigation.
I think you watched too much Sherlock.
Yeah, Sherlock would have done this in his head. Oh,
Yeah, what?
blah, blah, blah. He walked this and jumped through the window and turned around. Yeah, okay.
Maybe the dad hired a hitman.
Yeah, the dad hired a hitman, which is the simplest solution. Right, so the alibi is worth checking out, need more investigation. That is your professional opinion.
What?
So, alright, so the rest of these we're going to do when you can see an example of the kind of problems that you'll be expected to do. And these are actually problems from past finals, so you know you will need to know this. This is the last thing we're going to do in 2.3. We'll do that next time. So bring this back with you. And we'll end with a quiz.
This guy. This guy. This guy.
Wait, can we use our calculators?
No, you won't need calculators.
We'll use our notes.